So my name is Becca Steorts. I'm an assistant professor in the Department of Statistical Science and Computer Science at Duke University. And I'm going to give a tutorial on Bayesian entity resolution methods. And I sent out a link in the chat regarding where you can access all of the materials of the course. And I also posted it this morning. If you need to find it, all of the materials are here. There's 4 different parts of it. And I'll be the speaker for today. There's lots of contributors that former postdocs, PhD students, and current PhD students that have contributed. And there's an abstract about what I'm going to talk about and some different overviews of the different parts. The first part is just giving an overview of the different parts of work that I've done with my collaborators, my PhD students, former postdocs, in a Bayesian type of framework. So I'm going to highlight these, especially on case studies, and try and talk about insights. There's a link to each slide deck. Then I'm going to talk about more practical different types of entity resolution that have been done in the past, and talk about evaluation metrics, and talk about a small example to illustrate how these have been used in practice and how comparisons have been done. And then I'm going to talk about some recent work that I've done with a PhD student, Neil Marchant, who just graduated and was jointly advised with Ben Rubenstein. And this paper just appeared in JCGS. And this is on a very scalable type of Bayesian entity resolution that scales into the millions. And we've applied this to a case study at the decennial census. And then finally, if those that are interested, I can perform a demo of this particular method and how it works in practice. And I'd finally just like to thank the NSF Career Award and a Sloan Research Grant for supporting my work. Finally, if anyone has any questions, I really like interactive types of talks. I'm very sorry this isn't in person. So if you have a question, feel free to raise your hand and I'm happy to allow you to talk, or one of the ISBA members can allow you to speak and ask your question verbally instead of over the chat. Okay. So what I'm first going to talk about is different types of entity resolution, why it's used. It's used in many different contexts. It's used in human rights applications. It's used in medical data. It's used in official statistics data. And as we collect more and more data as a society, it's used pretty much in many different industrial settings. It's used to collect information about people, about businesses, about different entities, about objects, all different kinds of things. So the big question is, what do these data sets have in common? There's duplication in the data. The amount of duplication is typically small. And before we can apply any inferential or prediction method, duplicate records have to be removed. So understand this a bit more carefully. I like to talk about what's called the data cleaning pipeline. And what I'm going to talk about today is entity resolution, where entity resolution is just one small part of that pipeline. So what happens is if we think about survey methodologists, they collect data. And this data goes into different data sources or databases. And typically it's not aligned, it's not nice, and it has to be mapped to different sources made up of schema that are mediated or aligned so that we can work with it. So this is the first part of the pipeline. The second part of the pipeline is known as blocking, which is a type of dimension reduction. And we need this type of dimension reduction to avoid all-to-all record comparisons. So blocking is where we place similar records into partitions, or rather blocks, so that we don't have to do this giant red comparison of all-to-all record comparisons, but we can instead now look at these blocks and perform entity resolution within each block. And if they happen to be separated, then we can perform entity resolution embarrassingly in parallel and get nice speed ups. Now, what is entity resolution? Well, entity resolution which is also known as record linkage or de-duplication, is where we're going to identify records that refer to the same entity. And we often do this in situations where we don't have a unique identifier. Now here we get clusters of records. So we think that these clusters refer to the same entity in the middle. Now we're not done after this step, unfortunately. So we have to move to the step of canonicalization, merging, or data fusion. And this is where we merge records that refer to the same entity. So this is where we find a representative record for this one, the one that we think is the most representative, and that creates a representative data set. And finally, we end up with a representative data set, or what we call integrated data. And now we can finally put this into a linear regression, a logistic regression, and find our predictions or inference that we're interested in. So in short, this is a very long, complicated pipeline, and entity resolution is just one part that is incredibly important. And this is the emphasis of this particular tutorial. So as I already mentioned, entity resolution is the process of merging together noisy, but crucially structured databases to remove duplicate entities. And as I mentioned, they're often in the absence of a unique identifier. Of course, if we have a unique identifier for every single entity, then we can call it a day and go home. There are many names for entity resolution across all different types of literature. Some of these names are record linkage, there's de-duplication, there's duplicate detection, there's data matching, there's data integration, there's data cleansing, and I could go on. Okay, so I'm going to start with giving some foundations in terminology. So I like to think of this problem as being a graph with no edges. So I have, for example, an instance of myself, Becca Steorts. So here I have a representation of myself with my name is a K. My real name is Rebecca with two C's. And then I have another entity over here that's Becky. And so we'll get to that in just a moment. And so the goal of this problem is to figure out, well, is this Becca Steorts and this Rebecca Steorts the same person? And if they are the same person, I'm going to say that they're co-referent or that they're a match. And if they're not the same person, I'm going to say that they're not co-referent or they're not a match. Now, it just so happens that my mother's also, we have the same first name and last name, but she goes by Becky, whereas I go by Becca. So in this instance, I know just by a priori knowledge that we're not the same person. And I know this by, if I looked at the attribute or feature information behind this node information here. Now, what I'm also assuming is that I have multiple databases. I might have duplicates within and across the databases. And again, as I said, I might have information behind. So behind each node here, there's information about the individual. So here I have an address. So this is publicly available regarding my address at my Duke office. And this is some publicly information available about my mother. So for example, she might live at this particular street in Charleston, West Virginia, and she has a redacted or missing phone number. And so if we looked at this, we would say manually or using our visual eye that we don't think these two people are the same. And again, this is just based on my a priori knowledge. Of course, we want to be able to use some sort of sophisticated algorithm model to be able to do this in a much more sophisticated and automated way. Now, what is the goal of entity resolution? Where our goal of entity resolution is to be able to say, well, these two individuals, even though there's typographical errors and missing data, is a cluster of size 2, and they refer to the same entity or person. Now, it doesn't say which is the most representative. So remember, if I go back to the data cleaning pipeline, that's resolved in canonicalization. So again, to find the most representative record, you have to perform this canonicalization, data fusion, and merging. One of the most common and most simplistic ways of doing this is taking a record uniformly at random. Of course, there's all kinds of problems involved with that. And that's why canonicalization gets its own piece of the literature. So in this talk, in this tutorial, I'm going to focus on the entity resolution task of the data cleaning pipeline. There's lots of different references regarding from the computer science, machine learning, and statistical literature. My PhD student and myself have a recent archived review paper on this literature, which covers trying to thread the needle more between the statistical social science framework as well as the computer science literature. So what are some challenges that we have to think about when we're approaching this particular problem? Just see. Okay. So there's four main challenges that I personally think about. One is has to do with the costly manually labeling of data. So there's lots of amounts of manually labeled data that are typically needed for any type of fully or semi-supervised learning method and evaluation. These are difficult to do. There's not one way of always just manually labeling the data. So if I go back here, if I were to manually label this, I would say that these are not a match, but someone might say that, oh, this is my office address, and maybe this is where I grew up, and they might think that this is a match. So we can see how errors can be easily added into manually labeled data. There's also scalability and computational efficiency concerns that come into play. So if we have approximations that are required to avoid quadratic scaling, we need to ensure the impact on our accuracy is minimal. And so to me, this is quite important. And this is something that I'll talk about when I talk about the end-to-end entity resolution or the distributed approach that Neil has proposed. There's also a great limited treatment of uncertainty. So given inherent uncertainties, it's quite important to output predictions with confidence or credible regions. So this also motivates taking a Bayesian approach here. There's also a lot of procedures that provide unreliable evaluation. Again, this motivates taking a Bayesian approach because you have uncertainty propagation for free under the Bayesian paradigm. So again, standard evaluation methods will often return imprecise estimates of performance. So next, I'm going to head into a little bit of the history of probabilistic record linkage. And again, feel free to interrupt me if you have any questions. So one of the first published papers was by Halbert Dunn, and he was the chief of the National Office of Vital Statistics from 35 to 60. He was a leading figure in establishing a national vital statistics system in the United States. And he was very key in defining what record linkage really was in this early period where it was being defined. And specifically, he defined it as being a task of assembling together all important pieces of information which refer to the same individual. So if we go and look at the first page of this paper and the abstract, he talks about how people are individuals who come into the world are basically made up, they're creating books of life, and their particular book or chapters are starting with birth and are ending with death, and they're meeting up with these records of principal events of life. And I quite like how he frames this because it makes me think of how things are done now in official statistics, and how he framed things in the National Office of Vital Statistics, how things are done at the United States Census Bureau. And so this is one of the key and seminal papers that I think of when I think of record linkage. This paper led to a paper written in '59 in Science by Newcomb, Kennedy, Oxford, and James. And this was one of the first really automated methods that was used by statisticians. And specifically, they were linking vital records here. They proposed a probabilistic record linkage method and implemented it on the state of the art at the time. So I like showing this to my students because they don't really know what a computer looked like in this day and age. So you can contrast this very easily to the tiny laptop that I'm using right now. So this was called the Datatron 205. It was quite fast for the time period. Of course, it's quite slow now, but this was progress for this era. This paper was quite seminal because it then led to one of the most highly cited papers in the statistical literature, which is by Folge and Center from '69, which appeared in JASA. And this was a paper that was built on a decision theoretic framework where they really formalized the ideas that were proposed by Newcomb and his collaborators. So specifically, at a very high level, one determined if two records are a match using a likelihood ratio or hypothesis test, and they determined if they were a match if they exceeded a specific threshold. Now, this threshold is very sensitive. There's all kinds of details that I'll get into in the next lecture regarding the Folge-Sumter method. And many advancements and further proposals have made to the original paper. However, I'm going to focus on more modern approaches and Bayesian approaches, especially given that we're at the ISBA World Meeting, that are known as graphical entity resolution that my group has worked on recently. So at this point, I'll kind of stop and pause and take any questions if there are any regarding the setup or the history or anything like that before kind of continuing. Okay, well, I'll continue on with the graphical entity resolution if there aren't any questions. So the graphical entity resolution or the graphical Bayesian entity resolution that we have proposed is building off of Kopis and Hilton from 2001, as well as Tancredi and Liceo from 2011. So there's a series of papers, Steorts, Hall, Feinberg, that appeared in AI Stats, as well as JASA, and then a solo paper that I wrote with accompanying code on CRAN that appeared in Bayesian analysis. And this model is quite general. So it assumes there's an arbitrary number of databases, there's records within the database, and there's an overlapping number of features. Now, the data can be categorical or textual. Now, what we're going to assume is that this data is going to, we're going to cluster the data to a hypothesized latent entity. And we're going to link it using what we call the linkage structure. So if these match, then it's going to get the same edge from the linkage structure. As I said, the data can be quite general. So if it's categorical, we might assume, we would of course assume that it's multinomial with some parameter theta L, and then we can put hyperparameters on that. We assume that the data is distorted. So it has some distortion parameter Z with a distribution on here. So it could be the hit and miss model, or it could be more generalized from that. Then it has a hyperparameter beta L on here with other hyperparameters. And so depending on how complex you want to be with the model, you can make this model as simple or as complex as you would like. So you might be wondering why would you want to take this approach? So I have 10 reasons why. So it handles any number of databases simultaneously. So by this, it handles duplicates across and within simultaneously. It handles both categorical and text data. It handles missing data. The uncertainty quantification of the entity resolution task is natural because it's Bayesian. Transitive closures are nearly free. It has very sound theoretical properties, which I'll showcase in a few slides. It can scale to databases that contain millions of records. It generalizes to a wide variety of applications, which I will also showcase. It has equivalent or better performance than alternatives. And all software is open source and freely available to nonprofits. So to illustrate the graphical model just a little bit differently, if I'm thinking about the nodes are going to be the data points, this B down here is the latent entity, the Y, and the lambda or the linkage structure are the black edges. So I'm going to cluster the records. The model will cluster the records it thinks that are similar to a latent entity here, B, and the labeling is agnostic, or it doesn't matter. So this could be a B, a Becca, a 1, something else. And then, as I said, these are the links that are coming from the linkage structure. Now, this, you can imagine that this is just one iteration of a simple Gibbs sampler. So if I keep going, now I'm going to separate the Rob Tibshranis from the Robert Tibshranis from the Ryan Tibshranis. So now I have the Robert Tibshranis that are clustered to this latent R, and I'm going to keep going around, in this manner for the first Gibbs iteration, and then I'll repeat this for all Gibbs iterations until I reach convergence. Now, of course, we can speed this up using different types of samplers, but I just wanted to explain this using a traditional Gibbs sampler. This was one of the first applications we applied the method to, which was in Steorts, Hall-Feinberg, 2016 in JASA. Here, we're looking at a longitudinal medical data set that's made up of 3 different waves of years. The total data set is roughly 60,000. What we're able to see here is this is a completely categorical data set. So we're able to see that each cluster is satisfying transitive closures. So we're getting clusters of records here after the duplicates are removed. That is akin to the toy example that I showed you right here. So we're getting cluster sizes. Now you may be wondering, what is the coloring? So the green coloring is what the unsupervised model believes to be matches, so high probability matches. And the red ones are ones that we should push to clerical review. Now I just want to iterate that there are a lot of red ones because it is a categorical data set. Now, there are some pictures that we can illustrate regarding the fact that we do have ground truth in the sense of which types of edges or records we are getting wrong, such as false positives or true positives and things like that. And those can be found in the JASA paper. So I told you that we have theoretical bounds or theoretical guarantees. So these are the Bayesian graphical entity resolution models are the only ones that I know of where you can prove some sort of performance bound in closed form, and then also illustrate using simulation that you can actually how close you are to getting to that bound. So here on the left, this is all for the categorical data of the Bayesian graphical entity resolution methods. So if I look at this, what I'm looking at is the gold here is the true bound, and these are, for example, Gibbs samplers and things like that. So you can see that the bound here is quite loose for all of the parameters. So why is that happening? Well, it's happening because the data is categorical. So we should always expect to have a quite loose bound. And I should mention this is the log error, so it's not as far as away as it's not as loose as it maybe looks. But the interesting thing, and I think this is quite common sense, is as soon as we add at least one string value, which is this right panel over here, as soon as we add at least one string value, the bounds are very, 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 very tight. And so this appeared in AI Stats in 2017. And again, you can look at the bounds, and again, you can make, I think, these nice plots. And again, to my knowledge, this is the only type of models that you can do this for in the literature. So one of the last points I want to talk about is, well, so I mentioned this model, this type of model here. This model by itself does not scale well, so it's quite slow due to the high dimensional parameter space of the lambdas. So a recent goal that I worked on and was led by Neil Marchant, who, as I mentioned, just graduated. So our goal was to scale Bayesian entity resolution methods to millions of records. And crucially, we didn't want to sacrifice the accuracy, and we wanted to provide uncertainty of the entity resolution task. And this ended up being incredibly difficult to do. So what we proposed is a scalable joint Bayesian model for the blocking and performing the entity resolution task. And in this sense, because it's a joint model, so it's a joint model over the blocks and the entity resolution, the error from this joint task is measured exactly. So I'm going to highlight a few things from this paper, and then in the third part of the tutorial, I'll dive into this a little bit more deeply. So this is just a comparison of some convergence rates for de-blink, which is the distributed version, versus the predecessor blink, which is my Steorts 2015 paper. So if I look at the teal is the distributed version, and blink is the one on CRAN. So we see after 11 hours, we're failing to converge. And this is on the RL data 10,000 set, which is available in CRAN. Now, if I look at de-blink, it's reaching convergence almost immediately. And then we can actually break up the aggregate distortion by birthday, birth month, birth year, first name, and last name. And so we can see what's really giving us trouble. But as you notice, for the teal, for de-blink, it's reaching, the trace plots look very, very nice, and the way that we would expect, whereas blink is, again, failing to converge after 11 hours. We can also do assessments of different pairwise linkage performances for de-blink versus the original Fulgin-Center method. So here we're looking at the pairwise precision recall and an aggregate of this, which is the F1 score. I'm comparing this to Fulgin-Center, where I'm giving it basically as little as a small amount of training data as possible. Of course, the comparison is completely unfair because with Fulgin-Center, I'm giving it training data. So this data set here is a synthetic data set that's based on the Australian Bureau of Statistics. So this is something they use for production and that was shareable. If I look at Fulgin-Center with a very little amount of training data, we can see that the pairwise precision and recall just completely drop. And this should be concerning because if I just raise it, by an order of magnitude, it illustrates the sensitivity of the Fulgin-Center method. For the voter registration data set of North Carolina, this is a real data set of voters in North Carolina. We can see that this one's pretty stable. However, we're doing pretty well compared to it. And for the National Long-Term Care Survey, again, we can see the sensitivity of the Fulgin-Center method from varying these different training points. So this data set is around 60,000, this is around 600,000, and this is, again, around 600,000. This is something that we cannot illustrate with the Fulgin-Center method, so we can't look at posterior standard errors. So here I'm showing a posterior bias plot where I'm summarizing it for all of the data sets we looked at. So here I'm looking at the Australian Bureau of Statistics data set, the North Carolina voter registration data set, the National Long-Term Care Survey data set. This is a small synthetic data set, and this is a categorical data set from the Bank of Italy from 2008 and 2010. Now, what we have here is I'm looking at the prior and the posterior, and there's a credible interval on here. So what I can see is that for the ABS employee and the voter registration data sets, these don't have a lot of error in the updated posterior. And this intuitively makes sense because these have quite a lot of string data or textual data in them. Now, if I go to the National Long-Term Care Survey and this other survey here, these are both categorical data. And so I have here 20% to 30% error. And this is pretty standard for these data sets because of the amount of categorical data that I have. So this is also not surprising. The RL Data 10,000 data set has quite a bit of missing data in it. So 10% error for this data set is also not surprising. The one thing that does happen, the posterior estimate is incredibly sharp and typically underestimates the true number. This is something I theoretically showed that happens when you use a uniform prior on the linkage structure. Back in my JASA paper, this has since been addressed, but there's a balance. There's a balance between using the uniform prior and more robust priors in terms of computational complexity when scaling. And that's something I'd be happy to talk about at the end. These are results for a case study that we did on the 2010 decennial census, where we merged it with numident data. So this is basically based upon Social Security data in the state of Wyoming. So in total, the entire data of merging the census data with the numident was a little over 1 million here. We have pairwise evaluation measures. So the precision and recall are 0.97 and 0.84 with an F1 score of 0.9. The posterior mean is rounded to 616,000 with a standard error that is rounded to 5,000. And we can compare this with the adjusted count that was published in 2010 by the census. So finally, I'd like to briefly comment on something that is known as the microclustering property. So specifically, the microclustering property is something I defined in my NSF Career Award, where as the number of records grows, we find that the size of the clusters is growing sublinearly. And we can kind of see this here. So this is meaning that infinite dimensional BNPs are going to be inappropriate for these types of tasks as the number of records is going off to infinity. So we can see here that if I look at a Dirichlet process, it's missing these small clusters here. The Pittman-Yor is also missing these small clusters. But if I look at these proposed models that we looked at in Benecourt, Zanella, and Steorts 2021 JASA, we can see that we're able to capture these small clusters. And what we tend to see in record linkage problems is we tend to see what we see here. We tend to see a lot of small clusters, or what we call microclusters. Now I'm going to briefly just talk about some case studies that have been applied to human rights applications. This has been a focus of my work and something that's been very important to me. I looked at a case study of the number of casualties in Syria with Betty Chin and Anshamali Shirastava from March 2011 to April 2014, where we found the standard error in real time. And this matched the results of the Human Rights Data Analysis Group, HRDAG, and this was a paper that appeared in the Applied Annals of Statistics. This is something that I would very much like to come back to and restudy for updated data. This is ongoing work with a PhD student of mine and Google Fellow Brian Kundinger. Here, what we're doing is we're looking at a more scalable version of CDNLA 2017, which is a Bayesian version of Fulgian Center. So Mauricio's version is known as beta record linkage. We're trying to look at fast beta record linkage. So we're trying to take CDNLA's very nice model and scale it to see how far we can scale it. So here we're looking at a case study of El Salvador. So we see that the posterior distributions are somewhat similar. We're underestimating the number of documented identifiable deaths. The thing that we really come up with in terms of an advantage here is that the method of Sedinley is not able to scale to something like the National Long-Term Care Survey in the hundreds of thousands, whereas we're able to with some computational tricks. So this is something that Brian is really pushing and working on for his thesis. And then finally, my PhD student, Olivier Bigned, has been working on applications of human trafficking. One of them has been in the United Kingdom, following on some important work that Bernard Silverman did. Here, we've been looking at population size estimation for different and popularly used models in the MSE literature. These can have duplications in them. And here we're just looking at the sensitivity of the different types of methods that you can get here. And we're trying to come up with principled ways that we can, principled advice that we can give to practitioners that are working on this problem, not only for the UK, but for all of the publicly available data sets, providing sensitivity analysis as well as other things. And this is submitted work that Olivier has just gone through. That has really nice R packages available. So the rest of the short course, so we just completed the first part. Next, I'm going to do a deep dive into entity resolution. So I'm going to talk about Philligian center. I'm going to talk about blocking. I'll talk about different evaluation metrics. I'll talk about robustness. Then I'm going to talk about distributed Bayesian entity resolution or end-to-end entity resolution and the paper that Neil worked on. And then for those that are interested, I'll talk about some demos and how you would actually run this in practice. So there's some other materials that may be of interest after the completion. So we have a review article I mentioned. There's lots of software that's available that my group has put out that's all in one place. And there's a much longer entity resolution tutorial on both Bayesian and non-Bayesian entity resolution methods for those who want to take a deeper dive. So thank you very much. I'm happy to take different types of questions, and I'm happy to have a conversation and also unmute everyone. Oh, so there was a question if I could repeat the microclustering property. So in general, the microclustering property, it says that as the number of records is increasing, we expect that the size of the clusters should be growing sublinearly. So we shouldn't expect a power law growth. Does that answer your question, Thias? If not, you can raise your hand.
Hi, could you just explain to me a little bit more what means that this sublinear rate, that the size will grow?
So not super linear, sublinear.
Sublinear, sorry, yeah.
So specifically, so are you familiar with Bayesian non-parametric models?
Yeah.
Okay, so specifically, instead of having a power law growth, we will expect, so more precisely, we will expect that, so let's suppose that, let me just pull up something really quickly so I can define, this for you. So this is just one way that you could define it right here. Can you see this?
Yeah.
So a formal way to define it is if you have a sequence of random partitions C sub n, then they will exhibit the microclustering property M sub n, where M sub n is the size of the largest cluster in the random partition C sub n. And it will exhibit the microclustering property if C sub n, if the random partition implied by that model satisfies the above definition. Now, you can either look at some of those models that satisfy it. You could look at the NIPS paper that I referred to, or the recent JASA paper that I just referred to for more details. I could also talk offline with you if that's helpful.
No, I got it. Thank you so much.
Okay, sure, absolutely. Any other questions? Okay, well, I'll stop this. I'll go ahead and stop the recording and stop the first session in case anyone wants to ask me a question that's not recorded. So the second part of the tutorial is what I call a deep dive into entity resolution. As I mentioned before, there's a lot more resources that I've posted if you're interested into exploring these topics in a lot more detail. So I'm just going to remind you again that entity resolution, record linkage, or de-duplication is joining multiple data sets to remove duplicate entities, often in the absence of a unique identifier. And so let's talk about for a moment why this problem is so difficult. So suppose we have a total of M records in D data sets, then we're going to seek models that are much less than O of M squared, so much less than quadratic. And we're also going to want to find models that are reliable, accurate, fit the data well, and account for uncertainty of the model. So if we think about this, 1 and 2 really go against each other. And they make record linkage or entity resolution an incredibly challenging problem. So if I think about the literature, most of the literature either accomplishes 1 or accomplishes 2 and doesn't really accomplish both. So I want to go over a little bit more terminology just to break this down a little bit more. So some of the literature is broken up into de-duplication, record linkage, and some of the literature will try and conquer all of it, which is entity resolution. And then I'll talk a little bit more about blocking. So de-duplication is where you cram all of the data sets that I had before into one list. So why would you want to do this? So the reason you would want to do this is for computational complexity. So instead of having a quadratic problem, I now only have everything in one database, and everything is more computationally, is much faster now. A lot of the literature can also be grouped in the case of deduplication. So common examples from academia and industry can be grouped into logistic regression, random forests, support vector machines, Bayesian adaptive regression trees, or locality sensitive hashing. So these are the kinds of examples that will lump everything into one database. Now, what do you lose here? Will you lose if there's dependencies? Or if there's dependencies that you need to take into account across the databases, you're going to lose this here. So it looks like someone joined late. So let me just post here the materials. of the short course again. So this is what I have referred to. I referred to this before as the entity resolution graph. So again, remember, de-duplication refers to duplication within just one database. Record linkage refers to duplication across multiple databases. And entity resolution refers to duplication across databases and within databases, meaning the whole graph. So when I talk about typically my work, I'll be referring to entity resolution. But if you look at the literature in general, it may be referring to de-duplication, record linkage, or entity resolution. And so you have to be a bit careful in understanding what someone might be referring to. Now, we talked a little bit about blocking, but I wanted to come back to this. So one often prefers blocking due to the fact that record linkage or entity resolution problems require a quadratic number of comparisons. So if I think about a record being a pixel in this red graph, then that would be a record to record comparison. So that would be just one comparison. So if this is a database and this is the other database, then this would be an M squared comparison where M is the total number of records. Now, blocking is going to put similar records into the same partition. So this may be one particular partition here that could be created by the blocks where they just happen to be on the diagonal. And as I mentioned before, if they happen to be non-overlapping, then I can perform entity resolution within each block, embarrassingly in parallel. So I can put these on a particular server or core, and then I can have a lot of savings this way. Now, I'm not going to go into the details of different particular ways of blocking. I'll get into one type of blocking in the next tutorial or lecture that we used for our distributed Bayesian approach. But I'm going to assume that some method of blocking is embedded within a record linkage procedure, and it typically highly depends on the application. The most common methods used for blocking are often deterministic methods or probabilistic methods. So a deterministic method may be that, well, suppose that I blocked on gender, then I would end up with two blocks, for example, those on, if there's two genders, for example, those on female and those on male. I could block on things that are more sophisticated, where I might block on last name or first and last name initial. And so you could imagine coming up with lots of different types of deterministic blocking schemes. The downside of a deterministic blocking method or a deterministic blocking scheme is the fact that you don't know the uncertainty of the blocking method that is then passed to the entity resolution process. This is why most people work with probabilistic blocking methods. So a type of this would be locality sensitive hashing, where maybe I'm going to use a similarity type score such as Jacquard or cosine to decide whether records should go in blocks or go in a different type of a block. And I've put some different types of papers where a paper that I led with Sam Ventura, Mauricio Sedinley, and Steve Feinberg from 2014 is one of my most highly cited papers, reviews the literature and does comparisons, as well as proposes some locality sensitive hashing methods. And then we use some of these approaches in an application to the Syrian conflict in 2018. Now, what are some common methods or baseline methods for entity resolution? Well, of course, if there's a unique identifier, we can match on this, as I said before, and then we can go home. We could perform something like exact matching. So exact matching would be looking to see if each attribute or feature matches exactly. Or we could perform something like a likelihood ratio test or hypothesis test, as I described in the first tutorial, using the method from Newcomb et al. 59 or Folligate-Sunter 69. Now, suppose that each feature has a unique identifier, and we're sure it's accurate, supposing like a social security number, then we can uniquely match records based on this particular identifier. But problems will occur if the identifier is missing or has noise in it. So as an example, if I have two different versions of Steve Feinberg, in exact matching, we compare all the features and we decide if the record is a match if they agree on every single feature. Otherwise, the record is decided a non-match. And hopefully we can understand why this method is very bad for evaluation purposes. So we could also do something like off by one matching, off by two matching, off by three matching. So off by one matching is where we would say that these two records are a match if they agree, but all but one feature. Off by two matching is where we say they agree on all, they are a match if they agree on all records, but two. And so to generalize, off by K matching is where we decide they are a match if they agree on all but K features. So this isn't really great for evaluation purposes because the recall and precisions tend to be a bit wonky, or the false negative rate and the false positive rate tend to be a bit wonky. So it doesn't work very well for textual data. Now, if I come back to the Fulligan center method and elaborate on this method deals with only two databases. It assumes that there's no duplications within each database, but there can be duplications across the databases. And it does an all-to-all comparison of records. It does a Neyman Pearson hypothesis test with some threshold T. And if record I and J are above this threshold, then we declare these two records to be a match, and otherwise we declare them to be a non-match. Now, there's some particular issues with this method. It's computationally intractable. So to make it tractable, we have to end up using training data. We have to use something like the EM algorithm in order to scale it. Transitivity is also not preserved. So why is this a problem? Well, if I think about what transitivity means, if record one matches to two and two matches to three, then I want to create that transitive closure. If I think about hypothesis testing, there are, if I think about all the different closures that I could make, there are many different ways to do this under a hypothesis test. And so it's not really satisfying or one of the best theoretical frameworks for invoking transitivity. So specifically, if I wanted to extend this method to more than two databases, such as K databases, then I'm having to look at all different K configurations of the hypothesis test. And so it becomes incredibly intractable to look at that. So finally, I'd like to talk a little bit about evaluation metrics. So how do we evaluate performance of a particular record linkage method? So there's a lot of different things that we want to think about and look at. So we would like to look at the recall, the precision, something called the reduction ratio. We might want to look at the estimated sample size, the standard error of the estimated sample size, or other summary statistics, depending on our application at hand. We might want to look at the runtime or the computational complexity, the robustness to tuning parameters, different sensitivity analyses. We'd like to see if supervised methods are overfitting the data. We'd like to look at comparisons. There's other clustering metrics that we can look at if we're looking at a clustering algorithm, but it depends on what type of method that we're looking at in terms of these evaluation metrics. So here I'm just going to review true positives, false negatives, false positives, and true negatives. So true positives are pairs of data that can be linked in both the hand-matched training data, if we have this, which we refer to as truth, and under the estimated link data. And so I'll refer to the situation as being true positives. Pairs of data that can be linked under the truth but not linked under the estimate are called false negatives. In the third situation, we have pairs of data that cannot be linked under the truth but can be linked under the estimate, and these are called false positives. And then finally, we have pairs of data that cannot be linked under the truth and also not linked under the estimate, and we refer to these as true negatives. So the recall is defined as the number of true positives divided by the number of true positives plus the false negatives. So this can be written as 1 minus the false negative rate. The precision is the number of true positives divided by the true positives plus the false positives. And this is 1 minus the false discovery rate. The F measure is 2 times the precision times the recall over the precision plus the recall. We can also rate the specificity, or 1 minus the specificity if we want to look at this. There is a slight issue with using the false positive rate that's discussed in Peter Christian's 2012 book on page 169, as well as a paper that I have in Bayesian analysis, in terms of you can get misleading results from using the false positive rate. So we both don't recommend utilizing these for specifically entity resolution problems. So you can get misleading results if you use the false positive rate. So the false negative rate is recommended instead. The reduction ratio is simply measuring the relative reduction of the comparison space from the de-duplication procedure or hashing technique. It's a long formal definition. The basic idea is going back to this picture here. So it formalizes the amount of reduction, or the percentage reduction of going from this space to this space here. So as an example, the reduction might be 90%. And of course, you want the percentage reduction to be as high as possible without impacting the recall and precision moving forward. So you, of course, don't want to split individuals that are the same across blocks, because then you can't fix that mistake when you apply the entity resolution method within the blocks. There's lots of other evaluation metrics that we look at. So we look at summary statistics, such as the estimated sample size. We look at the standard error of the estimated sample size. We look at the runtime. We look at robustness to different tuning parameters. We often look at supervised, either semi or fully supervised methods over fit the data. So for example, the estimated sample size and standard error have to be defined for each particular method. This is often not due to do in practice, especially for Bayesian methods. Any method can be evaluated also for the runtime, so one can gauge computational costs. I always recommend to look at the computational complexity. Robustness of tuning parameters should be explored from a Bayesian and a frequentist perspective. Sensitivity analyses should be extensively looked at. It's also essential to make sure, as I said, that supervised methods are not overfitting the data, and to make sure that we look at comparisons of competitors in the literature, and to do these on as many data sets as possible to understand the generality of any proposed methods. So I'm going to look at an example on some synthetic data that's available in the record linkage package in R. It's also available in the Blink package on CRAN as well in R. And I'm going to compare this to many different methods according to the evaluation metrics that I've just laid out. So I'm first going to describe the data set, and then I'm going to compare the following methods in R. So I'm going to use the Blink method, which is from Steorts 2015, which appeared in Bayesian analysis. I'm going to look at then logistic regression for deciding whether records are a match or a non-match. I'm going to do then the same type of thing using random forests. And then finally, I'm going to use BART or Bayesian adaptive trees and see how these compare. So the data set is quite simple. It consists of 500 records. It has a very small percentage of duplication. This second first name and second last name contains all missing data. So I'm just going to look at this first name, this last name. It's all German names. And then it has birth month, birthday, and birth year. And I have a unique identifier. So this is a small data set where I can understand how well it's working. Given the fact that it's incredibly sparse in the amount of duplication, it does take quite a long time to run just because of the high dimensional parameter space that we're working in. So if I run the blink method on it in R, this is the posterior density for the estimated sample size. This is the false negative rate and the false positive rates. They're both very close to 0, which is something that we would like to see. It's also quite balanced between the false negative rate and the false positive rate. I can also look at a graphical representation to see how many false positives I have. I only have one false positive, which is here in the upper right corner. It's in red here. So I can look at different summary statistics and visualizations. I see again here the posterior is quite concentrated. As I mentioned in the first tutorial, this is because the posterior here is, this is because the prior and the linkage structure is quite concentrated, because the prior distribution on the linkage structure is a uniform prior. And this is consistent behavior that happens whenever you use a uniform prior on any of these Bayesian models. Now I'm going to look at comparing blink, which is completely unsupervised. I'm going to look at exact matching. I'm going to look at near twin or off by 1 matching. So here I can see how everything is skewed. So I have an FNR of 1 and an FDR of 0. Then I'm going to compare it to different situations for BART, random forests, and logistic regression, where I give it different percentages of training data. So if I start down here with logistic regression, I have 10% training data, 20%, 50%, and the full data. So you can see that as you adjust different types, as you give it different percentages of training data from more to less, things change quite dramatically. This happens as well with random forests and also with BART. We find consistently, and I have a slight typo here, this should say 0.04. We find consistently that our method overall has the most stable FNR to FTR, meaning balanced. And given the fact that we're not giving the method any training data, it's also beating the competitors of the supervised methods with BART, random forest, and logistic regression. So this is just one type of comparison that one might perform, looking at different types of competitors and making sure to look at different types of sensitivities here. Now, robustness is something that I've talked about. How do we make sure the method is robust? For a semi-supervised method, we want to make sure it's robust to different choices of the training and test data and any tuning parameters. For probabilistic and Bayesian methods, we want to make sure these methods are robust to choices of the hyperparameters or tuning parameters. So for the blink method, there's extensive studies on every type of fixed parameter in the blink method, and this can be looked at in the paper. So again, this can be explored more further in this 2015 paper and the Steorts-Hall-Feinberg paper, and finally in the Marchant 2021 paper, which I'm going to talk about in the third part of the tutorial. So I'd like to end on this. This is kind of a survey of different things that I like to look at and think about just generally when I'm talking to students or collaborators that are just joining with entity resolution types problems. I'm happy to take any questions if there are any questions about the talk. Feel free to raise your hand if you have a question or ask it in the chat. And if you prefer that I turn off or pause the recording, I'm happy to do that so that you might feel more comfortable. So I'm going to pause the recording for now. I'm happy to, again, answer any questions or just say hello to anyone if anyone, again, has any questions. So next, what we'll be covering is going to be the third part of the talk, and I will put this in the chat in case you're having trouble accessing it. So welcome back to the third part of the tutorial. So this is where I'm going to cover end-to-end entity resolution. This is joint work with Neil Marchant, Andy Kaplan, Ben Rubenstein, and Danielle Elazar. So as I said before, there are 4 parts of the data cleaning pipeline. The first is the schema alignment, and the last part is canonicalization. So in this paper, and in this talk, on part of the tutorial, what I'm going to present is, to my knowledge, the first joint blocking and entity resolution approach that propagates the error of the entire task. And this is pretty important because it allows the blocking errors and the entity resolution errors to be propagated all at once, so that if you wanted to pass them to the canonicalization task, you easily can. And as an example, in work with Andy Kaplan and Brenda Benacourt, we've used this method de-blink to use this in the canonicalization step so that we can understand how it works with integrating data and predictions for voter registration data. So I'm just going to review quickly existing ER methods, sort of what they are and some limitations. So we talked already about deterministic linking. We talked about probabilistic linking, such as Fulgi-Sunter, random forests. There's other types of methods that are very commonly used in computer science, as well as machine learning, such as deep learning models. There's also active learning models. And then another method that's being more commonly used now is a Bayesian Fulgi-Sunter model. So it's where we take the original Fulgi-Sunter model of the hypothesis test and we simply put some priors on it. Now, there's drawbacks to all of these methods. There's subjectivity in the setting any type of decision threshold. A lot of these methods require training data. There's often a lack of uncertainty quantification from using these methods. And I've just mentioned some of the recent developments that have been worked on in these particular areas. This is certainly not exhaustive. As I mentioned, there's a review paper that I recently, that's under revision with my PhD student, Olivier Bignette, that you might want to look at in case you want to look at other methods in detail. So I already went through the graphical entity resolution approach. I'm going to review it just very briefly, and if you have any questions, please let me know. So again, this is the approach that I worked on before, that built off Kopis and Helton and Tencria and Liceo. What I want to do is I want to be able to improve and build upon this type of framework. So this framework is quite appealing because it satisfies many important things. However, it doesn't scale well. So this method only scaled to about 1,000 records. And as I illustrated in the first tutorial, it failed to converge. So again, I'm just going to go over why I think this approach is a good one and why I think it generalizes well. It handles any number of databases simultaneously, and it's one of the only approaches to do this. It handles both categorical and textual data at the same time. It handles missing data. Uncertainty quantification is natural here. We get transitive closures basically almost for free. It's one of the only approaches I know that has very sound theoretical properties, both the microclustering property and the theoretical bounds. It can scale now to databases that contain millions of records, and that's the work that I'm gonna show you here. It generalizes to a wide variety of applications, so I'm also going to illustrate that more here. It has equivalent or better performance than alternatives, so that's some of the that's something I showed you in the last tutorial. And all the software is open source and freely available to nonprofits. And that link is, all of the software is on GitHub, and it's either in CRAN or it's available in Apache Spark. And we provide demos and help if you're having trouble using it. So again, this is how we kind of think about how this works. So I'm going to cluster all the instances of myself to a latent entity B. And then I'm going to cluster all of the Rob Tibshiranis to a latent R to make sure I don't pick up this Ryan Tibshirani. And then I'm going to keep going. So again, this is one iteration of the Gibbs sampler. Now, a Gibbs sampler doesn't work here. And the reason is because this linkage structure is very high dimensional. So our goal of this paper was to scale Bayesian entity resolution methods to millions of records. And we really didn't want to sacrifice accuracy, and we wanted to at the same time provide uncertainty of the entity resolution task. And this ended up being very difficult to do. So what we end up proposing is a scalable joint Bayesian model for blocking and performing entity resolution where the error from this task is measured exactly. So we have some key assumptions. So we assume there's multiple tables or sources. There's duplicates within and across the tables. We assume the attributes or features are aligned. The attributes are discrete. Now this means we can have categorical attributes as well as textual attributes. There are some missing values, and we assume there's no ground truth, so we can handle completely unsupervised. This framework is completely unsupervised. The output is going to be an approximate posterior distribution, which is going to be over the linkage structure, which is what we call lambda. So now I'm going to go over the kind of the nuts and bolts of the contribution. And again, this was led by Neil Marchant, and he just graduated with his PhD. So we're proposing a joint Bayesian model for blocking. So we're specifically blocking the latent entities and doing entity resolution. So a big component here is we're not blocking the attributes or the records, which is commonly done in record linkage, but we're going to block the latent entities. So I want to really highlight this because this isn't commonly done in practice. We're doing this for a very specific reason. So we're blocking the latent entities so that this is going to be amenable to a partially collapsed Gibbs sampler so that we can actually make this usable for distributed computing. So because we actually block the latent entities, we can look at these as auxiliary partitions. They induce then conditional independencies between the latent entities. And this will then enable distributed inference at the partition or the block level. Then we propose a blocking function that's responsible for partitioning the entities. And it does groupings. It groups similar entities together while achieving well-balanced partitions. The blocking function is quite general. In practice, we use, for example, a KD tree. Then we apply the use of a partially collapsed Gibbs sampler from Van Dyke and Park in the context of distributed computing. We had to change some things from Van Dyke and Park a little bit from the vanilla one that they use in their paper. And the details of that can be found in our JCGS paper. Then we do some things to improve computational efficiency even more. So we propose a sub-quadratic algorithm for updating the links that are based on indexing. We do truncation of the attribute similarities. So for example, if I'm comparing myself, for example, to Susan Paddock, I'm going to the algorithm will look at that, see that the names are not the same, and it will truncate that to nearly zero. It won't truncate it to zero exactly because that creates issues with the sampler. Then we propose a perturbation sampling algorithm for updating the entity attributes. This relies on the Vos alias method. It's basically a quick little trick that allows us to do really fast updates at the entity level. And that's pretty much the nuts and bolts of everything. Then we do applications to both synthetic and real data sets, and we do a case study on the decennial census from 2010 in the state of Wyoming. We look at sensitivity analyses, robustness, we look at the computational complexity and things of that nature. This is a graphical model of what we're doing. So we have attributes, records, and tables. The X's are the data. We're clustering this again to latent entities. So we have entities E and attributes A. We're going to block the latent entities to these partitions here. And then these partitions are going to form our particular blocks, which feed into the linkage structure. All of this here is pretty much the same as the original model before. So we have some distortion. That distortion has a parameter. It has hyperparameters. And then this is the missing data component. So as you can see, we've added in this joint model here. And this key component here is going to make this amenable to distributed computing. This was coded up in Apache Spark. It's back-ended in Java and Scala, and it's also being investigated for production at the United States Census Bureau. So, of course, the posterior for the linkage structure is not tractable, so we're going to resort to approximate inference here. We're proposing an MCN algorithm that's based on the partially collapsed Gibbs framework of Van Dyke and Park from 2008. We're going to use regular Gibbs updates for the distortion probabilities, which are the thetas, the distortion indicators, Z, and the links lambda. Then what we're going to do is we're going to apply marginalization and trimming, and we're going to apply these jointly to the entity attributes Y and the partition assignments for the linked records. If you've used partially collapsed skip sampling before, the order of the updates is incredibly important, and this is to preserve the stationary distribution. What does this look like in general? So for one iteration, for example, of the Gibbs sampler, we have theta. We update theta on the master. So this is an example of what the partitions or the blocks look like. So we update theta on the master when we broadcast it to the workers. Then what we do is we're going to update the linkage structure on each particular worker. So if we look in each particular block, the records can only link to the entities within their particular block or partition. So nothing can move across the partitions. Then in the next step of the partially collapsed skip sampler, what happens is now we jointly update Y and gamma on the workers. In this particular step, we can resolve issues or mistakes. So entities now can move and records are assigned to different particular partitions. So for example, if there's a mistake here, it can move here. And now we update Z or the distortion parameter. We calculate summary statistics on the workers and we update the master. So now you can see like there are things resolved across the partitions. Then we repeat this process all over again until we reach some sort of convergence, or convergences in quotations. So I'm just going to stop here for a moment to see if anyone has any questions before I continue on about the algorithm, before I go into tricks about the algorithm and going over the experiments. Any questions at all? Oh, great question, Ed. So Ed is wondering about the convergence of de-blink. Let me just make my screen a little bit larger. So blink can get stuck. De-blink does not seem to get stuck. So let me unmute you so I can. Hi, Ed, that's a great question. So the original model blink can get stuck in different local modes. We don't see that de-blink, the distributed version, gets stuck in local modes because of the partially collapsed Gibbs sampler and the use of the KD tree.
Okay, I was just thinking that you're going to get to, at the last step, you're sort of going from assignments to refinements of the assignments and then refinements of that, but it feels like it might be able to just sort of get stuck in a loop and be going around and around. Of course, you can stop it if you see that, but I was wondering.
We haven't seen that happen in practice. I have some plots in our JCGS paper, we have the most insane number of just, convergence plots for all kinds of different things in these high dimensional spaces. Uh-huh. We haven't seen it get stuck. It certainly could because the space is so high dimensional.
Right.
It gets very, very, very stuck in blink. So I can look at all kinds of different things with blink and look at where it gets stuck and then talk about why it's getting stuck. It also gets stuck with the method of Sedinlay. And it's getting stuck there because you're just using a regular Gibbs sampler. Uh-huh. But we don't see that happening with de-blink, and we think that it's happening because we're using the KD tree. We're getting very good partitions, and then it's moving.
Okay, great. Thank you.
Absolutely. Great question. Any other questions? Okay. So there's a question regarding, if I understand correctly, the algorithm is distributed in the sense that the summary statistics are computed in a parallel environment conditionally on the current parameter sampled values. That is correct. Yeah. So just to clarify that point, it's distributed and parallelized in this particular manner. For the actual algorithm, we have that more clearly laid out in the JCGS paper if you're interested in looking at the specification, or I'm happy to go over that at the very end of the talk if that's helpful. Oh, so there's another question that's quite good. So let me unmute Daniele so he could ask this. Daniele, do you mind asking your question out loud? So Daniele has a question. Has there been any kind of comparison to fully parallelized MCMC samplers? So he's thinking about Wasserstein posteriors, such as Sherestava and Dunson. So you can't really do something, you can't do something fully parallelized here in the sense of Sherestava and Dunson, to my knowledge. because of the way that the model is done here. So if I'm thinking correctly of what Sherstav and Dunson were doing, I think everything is in a categorical setting. So it gets more complicated because we have textual data. We have a different type of a high dimensional data structure. We have duplications. Does that answer your question? So we could certainly do something like fully parallelize the blocking and separate out the entity resolution, but then we're going to lose the joint model. And we've looked at something like that, but it doesn't work very well, and it's not very satisfying when you look at a joint model, because with a joint model, you're able to propagate that error exactly. Perfect. Okay. Okay, so I just want to talk quickly about some tricks for speeding up inference. So there's a couple of bottlenecks that might not be obvious from just thinking about the problem that I wanted to mention. So there's two bottlenecks. There's a linkage structure update that we have to worry about. And this is of the order of the number of records times the number of entities. And then there's another bottleneck, which is the entity attribute update. So this is the order of the number of entities times the domain size. So there's two different things we have to worry about here. And so this is why I was saying it's actually different from things that have been considered, for example, in the MCMC literature, because usually they don't have this entity attribute update. So we have a couple of solutions. So one of them is indexing. So we maintain the indices from the entity attributes to the entities. And then we maintain the updates from the entities to the linked records. So why do we do this? Well, this allows us to prune candidate links for a particular record. So this is sort of like a computational savings and is more of a computer science / machine learning approach that we use. As I said before, we're going to threshold similarity scores. So if, for example, if my record is being compared to Ed George's record, I'm going to threshold that to a low probability score, so I never have to look at it. And I'm going to hold that in memory and cache, so I only have to compute it one time. Finally, I'm going to express the distribution for the entity attribute update as a two-component perturbation mixture model. So the reason that I'm going to do this is this allows for me to update this entity attribution update in linear time. And so this is just much faster than expressing it as a hit and miss model. And this uses the those alias method. So we looked at lots of different experiments for this particular application. So we looked at both synthetic real data sets and a real case study. So we looked at the synthetic data set that's internally used for linkage experiments by the Australian Bureau of Statistics. We then looked at the North Carolina voter registration data set. So this is two snapshots from the North Carolina voter registration database that's taken 2 months apart. We then looked at a subset of the National Long-Term Care Survey comprising of 1982, 89, and 94. We're not able to look at all of the waves because they subsampled, unfortunately, on race. We then looked at a subset of the Bank of Italy survey on household income and wealth that comprised of 2008 and 2010. And then we looked at a kind of a very basic synthetic data set that most researchers look at to see, is this sensible? Does it make sense? This is provided in the record linkage package in R. So these are some of the baselines we looked at to see how is this working? How does it generalize? What kinds of things are we seeing? So this was implemented in the package that we called Deep Link. The baselines were done in Apache Spark. We ran experiments on a local server to see how it ran on a local server as well as on Amazon EMR. We mostly used a sample size of 10 to the third after a burn-in of also 10 to the third iterations and thinning. We kept roughly every 10th iteration. If there's deviations, they're mentioned in the paper. Again, we had 3 real and 2 synthetic data sets. Here's a summary of the different data sets. The ones that are starred are synthetic data sets, and the ones that aren't starred are real data sets. Here we have the total number of records. Here we have the total number of databases or tables. Here we have the number of true entities. So we have a unique identifier for each of these data sets. So we're actually able to figure out some evaluation metric or quality control after we run our fully unsupervised algorithm. We can look at various different, so this data set, for example, only has categorical attributes. This one has categorical and string. This only has categorical. This has only categorical, and this one has categorical and string. I showed this in the first tutorial regarding the pairwise recall, precision, and F1 scores. Here I'm just showing the first 3 data sets, but we have them for all of the other 2 data sets. Again, we compared to Fulgi Center under low amounts of training data. One thing to note is Fulgi Center is supervised and doesn't propagate the uncertainty error compared to Deep Link. I showed this before as well regarding the posterior bias plot. So instead of showing the posterior bias plot, I could also look at complete posterior distributions instead of looking at everything on one plot. So we can have full posterior distributions, look at the prior sensitivity analyses with those 2. As I mentioned before, these are incredibly sharp. One way to fix that is to put a type of microclustering prior on here, such as the ones that we've recently proposed in Benecourt, Zanella, and Steorts from 2021, which is to appear in JASA later this year. And that would allow for a distribution to be kind of more spread out. However, that would destroy the computational scaling that we have. This is the convergence that I showed earlier. We have very similar convergence plots for all of the different data sets. Ed asked a really good question. So I may just pull up the paper so I can illustrate that when I get to the end of the talk. So this is on the RL data 10,000 data set. This is without doing any partitioning at all. So we get much better benefits when we are partitioning or we're doing the blocking. So again, we can see that we're reaching, things are mixing quite well. They mix when we use different starting points. And this was checked incredibly thoroughly. One thing that we looked at that we thought was quite important was, does partitioning result in efficiency gains? The answer was yes, but to a point. So we measured efficiency using what's called the ESS rate. This is the effective sample size generated per unit time. The speed up factor is the effective sample size rate relative to a baseline without partitioning. So we did this for all the data sets. This is for the National Long-Term Care Survey. So here we observe a near linear speed up. However, we see it tapering off beyond 20 partitions. One way to fix this would be to use something other than a KD tree. However, then you would have to do some load balancing. Since with a KG tree, you get well-balanced partitions for free. And we're looking at different summary statistics here so that we can see that it's near linear and we're not biasing towards one particular summary statistic. This again is the case study that we, so I ran this during my sabbatical on the 2010 decennial census. So this has been released under a DRB by the United States Census Bureau. Again, this is where we, to my understanding, this is the first pairwise precision recall F1 score in the first Bayesian method, joint blocking Bayesian method that's been applied to this particular data. Here we have a posterior mean and the standard error, so you can see the adjusted count. We're currently working on applying this to other states, releasing this, and something that I'm wanting to do is also apply the same types of case studies to 2020 to look at the differences. And again, the size of this data was over 1 million. So this, just to kind of recap, this particular application illustrates how you can do practical entity resolution in a Bayesian framework and scale to easily over 1 million data points. The code is available on our GitHub page. There's also an R wrapper for those who aren't comfortable working in Java or Scala, but we found the code to be quite friendly. And for those that are interested, I'll be working on a demo and showcasing how it works on a laptop. If you're gonna run it in a full setting, you'll need to be working on a server or AWS or something like that. So thank you, and I'll be happy to answer any questions about the Deep Link paper or this particular work. Hi, Ed.
Hi, Becca. Yeah. So another Blink question. So does it, as it's moving along, one can imagine that you're pretty sure about certain linkages, but there are others where you've got information that you're not so sure. Can Blink spend more time on the ones that you're not sure? Does it adaptively do it, or is that too refined?
It doesn't do it adaptively yet. That's something we're working on. So we call that an active learning approach. What it does is it does give you at the end of the process, it gives you, you can output for each particular link the posterior probability of those unsupervised matches. So does that make sense?
Yeah.
And then you can send the ones that did not work to clerical review, for example. So something we're working on that's in progress right now is a more adaptive approach, or what I like to call an actively learning approach, to speed things up, where it can learn through the sampler over time.
So right now you have human intervention to sort of do that, but you'd like to do it automatically.
Yes. Yeah.
Great
question. So I'm going to, if there aren't any other questions, I'll stop the third part of the tutorial for now. If you have other questions, please let me know. I am going to pull up the paper in case anyone has any questions about diagnostics or anything like that. And I'll screen share that and put that in the chat link. So thank you so much for all your amazing questions. I really appreciate the discussion. So sad this isn't in person. If you have more, please share them. I love questions. And thank you again. So welcome to the fourth and final session on entity resolution. This last part is how to actually run de-blink if you're interested in running it in practice. I'm going to show you how to run de-blink if you're on a personal laptop or computer. It works the same way generally if you're working on a server. I've posted in the chat room where the materials are in terms of the instructions, but I'm going to show you on my terminal how I run it. Okay, so I've opened my terminal. I'm working in on a Mac. It works pretty much the same way if you're working on Linux, and it works pretty similarly if you're working on Windows. So I'm going to cd. I've already installed the package using the instructions on the de-blink webpage, and this is the Java and Scala version. So I'm simply going to cd into the actual directory where I have the de-blink software. And then there's only one line that you need to actually run everything. So I'm going to run this on RL Data 500 just to show you how you can run this on your laptop for something small. So I'm just going to copy and paste. So this is doing a Spark submit command. I'm going to do it locally, so I'm going to do it on one core. I have these different types of options that are described in the tutorial manual. I'm using Scala 211. I'm using a jar file that's been loaded and pre-built, and this is telling the system where the target file is. And there's a configuration file that gives the system all the particular settings. So I can go into here for the configuration and go through what the configuration settings mean while it's running. So now I'm just going to hit enter. It's only on one core. So if I have more cores, I could certainly run it on more. So I can see that it's created the block managers. It's starting my sample step. It's doing a sample size of 1,000. It's not doing a burn-in. It's doing thinning, and it's doing a partially collapsed skip sampler that we call 1. I can see that it's generating my new initial state. It's gathering statistics. It's doing the indexing that I talked about. It's writing different things to file, and it's storing them in diagnostics. Now it's generating the samples. So this takes the most amount of time, especially if you're only running on one core. So if I did this in practice, I wouldn't run it on one core. I'd run it on many cores. And so again, this will be the most time-consuming part, since I'm running it on a MacBook Air that doesn't have a lot of memory or space or anything. So while it's taking some time, I'm going to go in and update. I'm going to go in and look at the configuration file. I can show this to you. So I'm gonna share a different terminal screen just for a moment while this finishes, so it's still running. So if I look at what's in this file, I'm now gonna cd into the examples, and then I can look at the RL data 500.config file. So here, what I can see is I'm defining distortion parameters. So there's low distortion, there's a constant similarity function, there's the Levenstein similarity function. So you can see it has a threshold here of 7. The maximum similarity is 10. Then I'm telling the data what path to look in for the actual data file. Then I'm going to specify columns that contain different identifiers. So for example, the record identifier is the record ID, and the entity identifier is the entity ID. For missing values, I'll represent these using NAs. Now I'm going to specify different properties of the attributes columns used for matching. So I have this different convention here. I have birth year, birth month, birthday. The similarity function for all of these is going to be the constant one. This is using a distortion prior of low distortion. So for this data set, I think everything has pretty much low distortion. For name, I'm actually going to look at a distance function. So I could look at something like Levenstein or Jaro-Winkler. So here I'm looking at Levenstein, and I'm looking at this for first name and for last name. I'm setting a random seed. I don't expect to have more clusters than 10. I'm putting in the KD partitioner. I'm not going to actually use the KD partitioner because the data set is so small. So again, a value of 0 means no partitioning. This is the output path of where I'm going to store my results. And then these are the different steps that are going to be that will be performed. So this is the sample size. This is my burn-in interval, my thinning interval, and the sampler that I'll be using. So the metrics that I'll be looking at are pairwise and cluster-wise metrics. These are further defined in the GitHub file that I posted in terms of the documentation of Deep Link. The file names that I'm going to output are the cluster size distributions, the partition size distributions, a diagnostics file, a shared most probable cluster file, a run.txt file, and an evaluation results file. And I'm setting the fact that if I rerun this, it's going to overwrite it. And that's the end of the file. So this is the general way that all of these look like. It does checkpointing in case something fails and you lose your results. And now if I go over and switch my screen sharing. So for some reason, it's still running. So now we can see it's almost finished. So now it's finished. It's finished doing everything. So we know this because it finished the sampling and it wrote to disk. It finished writing to disk. It does all the summarization steps. It wrote the cluster sizes. So it has to do a lot of things. So if you're not interested in all of the files, you can save a lot of time by basically not writing some things to file. So now what we can do is I'll cd into the results file. And I have these different now files I can look at. So one of the most simple ones that you might want to look at if you haven't taken a look at something in a while is the run. So it gives you summary statistics. It tells you where the data files are located at, the record identifier. There's no file identifier. So it tells you information about what you did. It tells you your hyperparameter settings in case you want to reproduce this for a paper. It tells you your partition function settings. It tells you your project settings, where you save things to, and different other scheduled steps that you worked on. The basic evaluation results are stored in here. So this gives you the pairwise precision, recall, and F1 score. It also gives you the adjusted RAND index, which is a clustering index. That's useful if you're doing a type of clustering problem. The other things that are useful is this diagnostics CSV file can be used to do trace plots. We can look at the different cluster size distributions using this CSV file here. And Ed had kind of asked about, how we know that certain different clusters have different probabilities, and we can look at that through this shared most probable clusters CSV file. So those are the basic outputs that you're given. So what we do with these is these feed in to R through an R wrapper. And then we can make nice plots in R using these files. So just to give you a quick idea of what these look like. So the diagnostics plot will allow you to do trace plots for different feature distortions of the RL data 500 data set. We're able to look at the partition size for different MCMC iterations. So this is looking at all of the data sets that we have. And we can see that the balance here is measured in terms of the relative absolute deviation from a perfectly balanced configuration. And we have different numbers of partitions here. We can also plot the posterior bias plot that I showed you in our paper. Now, let's suppose you want to download everything from scratch. You can do this lots of different ways. I have some different ways of doing this in the slides that you can do it. So for example, you'll have to do different things. You'll need to have Java 8 on your computer in order to do this. So you'll need to check your Java version number. So you need to have Java 8. Then you'll have to get access to a Spark cluster. So you'll need to set up a Spark cluster either on your computer or So you'll need to either set this up locally on your laptop or put this on a server. There's different ways to put Spark onto your computer or onto a server, and these are the different. This is just one way to do it. There's also a pre-built version that we have that I'll show you on the Deep Link page. After you do that, depending on what type of shell profile you have to save some options to your shell profile. Different systems have different types of profiles. For example, I have a Z profile. So depending on what type of what you're running in your terminal, you might have a different type of profile. So if you're running Bash, Debian, Fedora, or RHL derivatives, you're going to be maybe in a Bash profile rather than the profile here. I'm on a ZSH environment, and so I'm in a Z profile. You'll also have to obtain a dblink fat jar file, which has this type of name here. It's going to contain all the class files and resources for dblink, and it'll be packed together with all the dependencies. You can download a pre-built jar file, which has been built against Spark 2.3.1. It won't work with other versions of Spark, so you have to make sure that everything's working together. You can also build it yourself. So you can build it instead using a tool called SBT. You have to install SBT from your system. We have different instructions for building SBT on Windows, Mac, and Linux. So this is just kind of one way of how you can install the dblink file using SBT. Once you have SBT, then you'll want to clone the repository. You'll want to CD into the repository and then run SBT assembly. And this should actually allow you to produce the fat jar file. Then this should allow you to run the command that I showed you in the console, which allows you to run everything locally on one core and produce the results for RL data 500. So again, this is going to run Spark in pseudo cluster or local mode with a core. You can increase the cores by changing local 1 to local n, where n is going to be the total number of cores. To run deep link on other data sets, you just need to edit the configuration file. Or if you're interested in running the other files, we have instructions for doing that on the deep link webpage. These are the outputs. So run.txt again contains all the details of the MCMC run. There's a partition state.parquet file and a driver state file that's going to store the final state of the Markov chain. So this is useful so that the MCMC can be resumed. So in this way, you can run the Markov chain for longer without having to start from scratch. There's a diagnostics file that I showed you that contains summary statistics along the chain, which can be used to assess convergence and mixing. There's also a linkage chain parquet file that contains posterior samples of the linkage structure. It's in a parquet format. Again, this is so that you could rerun something if you needed to using Apache Spark and you didn't have to start everything over again. The evaluation results have these pairwise precision metrics. There's the cluster size distribution file, which contains the cluster size distribution along the chain. The rows are the iterations and the columns contain the counts for each cluster or entity size. You have to request this in the summarize step if you want to get this. And then finally, the partition sizes.csv is going to contain the partition sizes along the chain. Again, the rows are the iterations and the columns are the counts. And again, this only will appear if you request this in a summarize step. So again, this is the command that you want to run in order to get these results. Then we can look at the different plots that I showed a moment ago to make sure that things look pretty sensible, and there's different kinds of plots. So this is just a small subset of what we looked at in the paper for the trace plot, for the load balancing, the posterior bias plot. So you might try and replicate these on your own. You could try and replicate the experiments in the paper. And then we could talk about running this for other data that you might have, that you might want to run the deep link method on, and things like that. So finally, I'll just open up So this is where we have all of the deep link code. It's pretty well documented. There's a step-by-step guide that includes building deep link from source and running it locally, in addition to the slides that I just provided. There's a lot of documentation. If you have questions, you're welcome to post to the issues page if you're having some sort of an issue. The specific guide is here. And this is a more extensive guide than the slides provide. And if you're interested in kind of doing things in pre-built forms, there are links to pre-built forms if you don't want to have to build them yourself. So there's lots of different ways to do this. There is an R wrapper, but it does involve having to go through all of these step-by-step processes because you have to use Spark. So you still have to go through this to run the R wrapper. So with that, I'll take any questions if anyone has questions. If people would like to try installing it and running it, I'm happy to also help you with that process if you're interested in doing that, or you can try it on your own later. And I'm always happy to set up a separate session with participants and help with debugging or any questions you might have about the software. So with this, I'll end this part of the deep link demo, and I'll stop recording, and I'm happy to answer any questions that you might have regarding anything in the tutorial at all.